back to it. We were talking about coefficient of discharge. This essentially means the energy contained by the exiting gases, or even gases entering the system on the intake side. But it's easier to look at it from the extra energy that's being pushed out of the exhaust port as soon as that opens, which is the event. It's called blowdown. All of the energy in the exhaust system comes from this event. There's no extra energy coming in anywhere else. If anything, there's going to be entropy and other losses to the environment that the engine's already experiencing, which is where we're gaining performance back from. So what do you have? You have this discharge, essentially. You have your inlet charge. You can also look at it as an exhaust pulse, an exhaust charge. You have your sonic effect. As soon as that exhaust valve cracks open, at the speed of the local speed of sound, you have a wave traveling out from the port. Whenever it reaches a cross-sectional difference, you'll have a reflected wave there. Now, this can happen from pretty much anything. So you have the sonic pulse that occurs in the header. This goes at the local speed of sound, reflects off of any change in area. This is where a lot of header tuning is found, in getting this to line up right at a certain RPM. And if there's anything about tuning, that one thing that's going to constantly come into play is what RPM are you optimizing, for what reason are you building this, and you might as well make all your parts work together. Do some odd parts work together with other parts. What's the percent difference? Sometimes it's null, sometimes it's very important. In my opinion, if the thing's not running right, there's going to be nothing that's going to be worse than that. So first off, having a good running, broken in situation. But most engines require a break-in period, so even if it's already bolted up for how it wants to be, even a NASCAR engine needs to break in for some period of time. There's a way to do that. You treat it right on break-in, then you got Italian tune-ups. But the energy, where is the energy coming from? It's the fact that the energy that an engine makes is pulsed. It's not a constant flow of energy. It's not a constant push of air, or whatever you want to consider it to be. Air is a part of it, but it's pushing and pulling. It's converting it into large amounts of pressure that has an energetic effect that can be used to benefit the other one that's not on that phase yet from this would have been lost energy for the whole system to work. Now, this is generally going to be down for a lower RPM. How do you make lower RPM torque? Nobody will tell you that. How do you make MPG? Nobody will tell you that. Nobody will tell you these things. They'll tell you how to. The easiest way to do is to make horsepower. You just add boost. I mean, every engine has how it's tuned, how much horsepower it'll make, and a boost curve. Like, and it should be another way to understand what the engine is doing, by saying going from 0 pounds to 1 pound of boost adds, then going from 1 to 2, and curve that out. And what's the gain from each boost figure would show you some engine efficiencies. It will be based on cam timing and where the engine wants to peak torque. But this has nothing to do with the airflow. So look at your Econoline Ford van. Big old V8. It's not the largest V8, but it's a big V8 with a tiny little pipe on it if you look at it, because it's only supposed to make power between idle and 4,000 RPM. CFM is not going to be an issue. And if you put a big pipe on that car, it would probably be a little bit weak down low, because you wouldn't get those benefits of part throttles and torque down there. You'd probably lose some MPG. Now, wide open throttle, you're probably going to make more power. I mean, wide open throttle seems to always make more power with the beams. But that may not mean. What I was saying is, for wide open throttle, on a dyno, the shortest, largest in diameter, shortest pipes, all that, tend to allow the engine to make the most horsepower at the peak figure, and also horsepower after peak at the top of the RPM range, depending on the engine. Now just going about it like that, you're throwing out all your sonic wave tuning, you're throwing out your inertial ram tuning, you're basically throwing everything out to try to, let's say, call it a YouTube, get a high YouTube number figure you could post on a forum or something, but it says nothing about drivability. Now, I'm not talking about actual people who do scientific work for us in documentation of what engines can do with different bolt-ons and different modifications, etc. Lots of people are doing great work with that, and they're doing the work in a way where they're not assuming or expecting what they they have the expectations, but they're not assuming like they know everything, they know what's going to happen. With that, we've been able to get a lot of information together based on what generally the engine would like, and how this all changes for RPM. So you have different flow regimes. The type of flow into the cylinder from a poppet valve is different at different points of the RPM range of the engine, because the aerodynamic characteristics of the airflow are different. Generally, velocity will increase until max flow is hit, at which point the velocity, there's no additional energy to cause these numbers to increase. Also, the efficiency. So two very important parts of this process of aerodynamic filling of a cylinder have to do with coefficient of discharge, which is basically, one would be a perfectly efficient flow in a port. Would be a coefficient, would be a number of 1. Now you can get values higher than 1. This is something that goes into where I'm trying to explain where this energy and this capability come from. Another 2 is port energy density. Now this is a figure you get that is actually can be represented in foot-pounds. The actual force that the airflow in the port has, the energy that has. Where does this energy come from? Of course, it comes from the gasoline combustion or diesel. Fuel in general. It doesn't have to be necessarily gasoline, but the fuel combusting in the cylinder, of course, in a gaseous state, produces energy. And what many people will say that an engine is a simple air pump, it's a very complex air pump, is what David Vizard would say. It's not a simple air pump. If it was a simple air pump, it'd be a ceiling fan. It'd be it'd be a bathroom vent fan that just has a constant CFM at a constant pressure based on how it's able to flow, based on the energy it's given to flow this, hence the pump. And it's constant, there's no pulsatile function. Now in an engine, you have pulses and wave tuning. So you have periods of time where lots of energy are released, then you have periods of time where there can essentially be no energy being released. And with that you have, excuse me, I'm all over the place here. With that, you have the ability to use the energy that you're not using for that specific event to help facilitate another one. This is where most of the percent gains and performance gains are found in an internal combustion engine, reciprocating piston engine. It can happen on other types of engines as well, but specifically a piston engine, the fact that the power stroke is very, very small amount of time, as well as all the other strokes, but it takes 720 degrees to complete a cycle. I'm going to go into it a little bit more detail. I don't want the video to cut, but we're going to keep this going. So for the application of those physics and technologies, you have a mode basically before the so-called VTEC. This is what VTEC EE is, where you only have one intake valve opening offset, of course, on the cylinder that has 2 intake valves, 2 exhaust valves, 4 valve head, 4 valves per cylinder head. You get this swirl because of the offset of that intake valve. Where the air is going in, it's going to hit and path the swirl around the cylinder, which allows it to do the stratified charge operation a lot better. By keeping the richer mixture near the spark plug with a progressively leaner mixture down the bore, without having lots of the same problems you can get with poor octane tolerance, with poor like firing and combustion characteristics. Those are largely avoided with this type of technology that's implied here. So what would this do? Well, of course, a standard tumble, both open valves at the same time type of operation would make more power, because at wide open throttle, even at low RPMs, it's still gonna get more cylinder filling and a lot higher pressure. Maybe not a lot, but there will be higher pressure developed, and this will lead to better wide open throttle torque figures at those RPMs down low like that. How often are you at wide open throttle? Not all the time. Still like part throttle operation. That won't really be felt with the stratified charge setup. So maximizing the port energy density with properly sized and flowing tracks before and after your so-called bolt-ons, because the timing of this cam and its architecture is going to want to make its peak torque down low. You increase pressure, you increase the torque, which of course leads to horsepower. Horsepower really needs to be multiplied over RPM. Essentially, you want to make peak torque and don't lose it. And if you really didn't ever lose torque, you'd get whatever horsepower you wanted if RPM wasn't limited. But of course, in our situation here with the Malaise build, we're trying to get that MPG. We're trying to have very high efficiency. We're trying to have a very nice mode of operation and lots of other niceties to build upon, while the engine basically Italian tunes up itself. A motor that's running for a while is a lot better than one that you just put together and then you want to go run a race on it. And I don't think you got to break it in. It needs to learn how to get all the parts to mate to each other in its own way as it goes about it. So maximizing the torque at those RPMs is critical. So you need to take those RPMs and learn how to make torque at those RPMs and know what your limitations are and what your application is. I'll keep going into this. We're going to keep showing the build, and we're just going to keep on going.